Welcome to the water sampling module. The topics in this module walk you through the options that you have when you go through the decision process on how to collect water samples. Topic 4.1 provides important information about sampling principles and stream hydrology. It presents an overview of the various methods you can use to collect water samples and an introduction to stream characteristics and flow patterns. Topic 4.2 explains the use of different containers for different analytes and communicates sample labeling conventions used in SWAMP and other programs. Topic 4.3 shows you how to fill your sample bottles directly with water from a stream when wading is possible. And Topic 4.4 gives you demonstrations of a few options to choose from when you cannot wade. Topic 4.5 demonstrates the specialized sampling techniques for specific needs. For example, ultra-clean samples for trace elements, or specific analytes such as chlorophyll A. Topic 4.6 is focused on the collection of field quality assurance and quality control, or QA/QC, samples, including field blanks to prove sample integrity and field duplicates to assess the reproducibility of the entire sampling and analysis process. Click on a topic to start, or click the Next button to see them in order. This module applies to all types of stations: streams and rivers, estuaries and wetlands, lakes, reservoirs, and bays and harbors, including open water stations. It is assumed that you already have a sound sampling design tailored for the purpose of the data to be collected, and that all sampling stations have already been selected for that purpose. As you can see by the activity highlighted in green on your screen, water sampling is performed after the initial observations and water quality measurements activities have been done. As the field operator, you often have to make on-site decisions regarding sampling access, representativeness of the samples, and other aspects of data quality. You also have to make decisions related to your safety and to potential dangers posed by working with contaminated waters. The purpose of this module is to show you how to apply the appropriate method to your situation and to provide information and guidance on each option. Some methods are demonstrated by short video clips. Click the Next button when you are ready to proceed. Water samples are chunks of water in sample containers, collected and taken for analysis elsewhere. Water samples can be collected in a number of methods, some of which are described in detail later in this module. All of these methods, though, fall into one of three major groups. The first, which is the most commonly used and preferred way, is by direct filling of the sample container. This means the same container that will be shipped to the lab for analysis. A handheld sample container is dipped in the water and gets filled. That is, water gets in while air gets out of the same opening. Variants of this method include use of devices that hold the container and allow for extended reach from a bridge, for example a weighted basket, or from the bank, such as a pole with a clamp. Another variant of the direct filling principle makes use of an air displacement device, which holds the sample container within its body and allows for sampling at a discrete depth. The second way includes the use of a device to grab or trap a chunk of water and then transfer the water into a sample container that will be shipped elsewhere. A bucket or a beaker can be used to grab surface waters, while specialized water trapping devices can capture the chunk of water at a discrete depth within the water column. Grabbing and trapping devices require thorough cleaning between sampling stations, and even between deployments to different depths at the same station. The third way employs the principle of pumping, where water is drawn from the desired depth or location by being sucked by a pump through a tube and into a container. The tubing always needs to be cleaned, and if the water sample touches other parts of the pump, those need to be cleaned as well. The peristaltic pump is most commonly used to collect water samples. Water samples are collected from a location in the stream where the stream visually appears to be completely mixed. Ideally, this would be at the centroid of the flow, which is the imaginary line that separates the flow discharge into two equal parts. It is often the most representative spot in the channel. When you are looking for a place to collect water samples, always look for the centroid of the flow. Stay away from side pools, backwater pools, edgewater, and side channels. Sometimes you need to record exactly where, that is, in which habitat unit, you collected the sample. A habitat is a defined stretch of the stream that has specific characteristics. For example, A riffle is a stretch of shallow water where rocks or other substrate elements are breaking the water's surface. Every stream can be divided into discrete habitat units, each belonging to a given habitat type. The next two screens show more examples. Click the button to view a video about stream habitats, flow patterns, and the centroid of flow.
Here we have an ideal variety of stream characteristics and different places to sample from. Starting from up here, we have a pool that comes into a mixed riffle with a log jam. Here the stream seems to split with a small island in between, splitting the water that could somewhat mix up the sample. This would probably not be the ideal place to take a water sample. Seeing that we have a variety of characteristics, we'll pan downstream to see what other possibilities we have. As we come downstream, we have a large riffle where the water is well mixed. Since the water is moving so fast here, it's probably an unsafe place to wade. We would probably want to go more downstream. Here we have a glide after the riffle where the water is still pretty swift, which is also a good thing because it's mixing the water column from various depths. Ooh. And here we have more of where the centroid flow is coming from the whole stream to a deeper depth, which would probably be the ideal place to take a water sample.
In a naturally flowing river, areas of riffles and pools alternate in a predictable sequence and at predictable intervals, which are related to the width of the stream. Riffles are areas where shallow water is rippling over rocks. Pools are deeper and calmer areas. Determining the riffle-pool sequence and stream width can give students an indication of the extent to which a given stream is out of equilibrium with the forces that create it. In most natural streams, the distance between riffles is equal to 5 to 7 times the width of the stream. A riffle is a place of shallow rapids. The water flows swiftly over completely or partially submerged objects to produce surface agitation, but standing waves are absent. Many of the streams you encounter, particularly in urban areas, have been altered. These alterations, sometimes called hydromodifications, may significantly affect flow patterns and may have measurable impacts on water quality. The choice of sampling location has to consider these alterations, and they must be mentioned in detail when describing your station. You can click the button to see more information about sampling location in Common Element C. There are many different types of sample bottles for specific analytes. The analyses dictate the volume of water necessary at each site, as well as the types of containers, the cleaning procedures, and the use of preservatives. The summary of sample containers, volumes, initial preservation, and holding time recommendations for water samples are found in Appendix D of the Swamp Quality Assurance Management Plan. This topic shows only the general approach, and the reader is urged to check out the details in the latest version of that appendix. The same is true for the way that samples should be labeled, and for the need to preserve them. Details cannot be specified in this topic, but it is your responsibility to make sure you get all the information that is relative to your effort. Click on a subtopic to start, or click the next button to see them in order. Sample container properties such as material, light absorption, and opening size are very relevant to the process of sample collection and to the properties of the substances to be analyzed. Glass and plastic sample bottles have different pore space and therefore are cleaned and store samples in different ways. Glass is often specified for organic compounds, while plastic is considered good for metals. Samples for analysis of nutrients and other inorganic water quality parameters such as alkalinity or hardness are also collected in plastic containers. Each type of container needs to be cleaned in such a way that it will be appropriate for the analyte and detection sensitivity of the analysis. Usually, the analytical laboratory will provide you with the appropriate pre-cleaned container, but you will need to get specific details on how to fill each one. Please refer to Appendix D of the Swamp Quality Assurance Management Plan for information on matching container types to your analytes. For analyses of trace metals and mercury at extremely low detection limits, even slight contamination has to be prevented. In that case, special procedures are used for cleaning and transporting the containers, and for collecting samples. Bottles are acid cleaned in a laboratory and are double bagged in a Class 100 clean air bench or Class 100 clean room. They are then stored and transported full of weak acid storage solutions and should be treated as a potential health hazard. Exposure to these compounds should be as low as reasonably achievable. When emptied in the field, the acid storage solution should be discarded into a waste container. Please see more health and safety instructions in subtopic 4.2.3. You probably know already that a full sample container without a label is a liability and is even worse than a useless sample. You might also know that it is impossible to write on a wet surface, that nobody can read what is written on a dark bottle, and that permanent ink is not always that permanent. So it will make sense to you to make sure that you attach the appropriate type of sample label, with water-insoluble adhesive to each bottle. Then, write all required information on the label while it is still dry. You can also fill it out before you attach the label. However, in some cases you may need to add the date and time later, immediately before you collect the sample. It may be necessary to cover the written label with transparent tape to protect the ink, and putting the tape around the bottle in a full loop will protect the label from being accidentally removed when wet. Now you are ready to dunk the bottle in water and collect the sample. Please note that a sample is a unique entity described by the station, date, and time at which it was collected. Several containers may be filled at the same time for different analytes, and they may all share the same sample ID. Many programs print the sample labels in advance, including all information except the time. Field operators choose the appropriate label carefully when at the station, then write the time and wrap the tape. If you want to do it the same way as swamp crews, contact them on how to fill out the label on each container with the station ID, formerly known as the station code, the event type, analyte, project ID, and date and time of collection. In most cases, swamp crews use containers that are pre-labeled. Because all sample containers collected on the same event may share the same collection time and sample ID, make sure that all containers are collected as close as possible to each other in terms of place and time. As you prepare the labels, write the same time, which corresponds to when you anticipate filling the first bottle, on all bottles. Prior to sampling, secure the labels by taping around the bottle with clear packaging tape. If you are not delivering your samples to the swamp laboratories, check out the requirements of your lab and your data tracking system. At a minimum, record your own station ID, or sample ID if it includes the station already, as well as the sampling date and time on the label. Adding your initials is also helpful. Water samples can be preserved to protect certain analytes from changing, being metabolized, or otherwise deteriorating. Laboratories often add small amounts of strong nitric acid to the plastic sample containers that will be filled with samples for analyses of total metals. Labs are required to attach a special warning label to such containers. In other situations, field operators add the acid to the samples in the field after collection. In any case, this involves handling very corrosive substances. Utmost care must be exercised. Always wear protective gloves. If you are filling containers that already have preservatives, never rinse the containers in sample water and never let the water overflow. Click the Next button when you are ready to proceed. Direct filling of sample containers is the most commonly used sampling method. It is also the preferred method because it minimizes the chances of sample contamination. This method is feasible in the majority of California streams during base flows, that is, when the stream does not contain runoff. Subsurface water samples collected about 10 centimeters or 0.1 meters below the water surface usually provide a good representation of the stream water mass. Sampling occurs directly from the sampled water body by wading into the stream and dipping bottles under the surface of the water. Normally, sample containers are rinsed with stream water 3 times before filling and should be opened and recapped under water. However, if you use a container with pre-added preservative, or if you collect a sample for SSC, or suspended sediment concentration analysis, you will have to use a different procedure. Please refer to the swamp field protocols for current information. This method can be used with different types of containers to collect samples for toxicity testing and for analysis of conventional water quality parameters, nutrients, organic compounds, dissolved metals, and other constituents. All bottles should be cleaned according to laboratory protocol. Personnel involved in field sample collection and processing should always wear protective polyethylene gloves. If the water is too deep, they should use shoulder-length gloves. Sample containers should be filled completely and immediately stored on ice. Please click a button to view a demonstration of the procedure it indicates.
Sean is now going to demonstrate the collection of an organic sample. He's using a 1-liter glass amber bottle. This bottle does not contain preservatives, and it will be rinsed 3 times with ambient water. So he will put the bottle under water, uncork it, allow it to partially fill, remove the bottle, agitate it, and then dispose of the rinsate water downstream and behind him. He will do this 3 times, each time putting the bottle facing upstream, removing the cap under the surface of the water, allowing it to partially fill, capping it underwater, agitating the bottle, and then disposing of the rinsate behind him downstream.
After the 3rd rinse has been completed, the sample is then collected.
And now he's collecting the sample. The bottle will be filled entirely. He will allow the bottle to fill until the bubbles stop. He will then cap the bottle underwater and trapping no air in the bottle. This is called a zero headspace sample. He's now checking to make sure there are no bubbles in the sample. It looks good, so the sample is complete.
An inorganics sample is now going to be collected. The sampler is looking for the centroid of the stream, usually somewhere in the center or where the deepest channel or the thaw leg is located. You can also tell by the flow of the water. You want to get a representative sample of the whole stream, usually in the center or the centroid is the best place. Sampler is now taking a grab sample, a subsurface grab sample. He's uncapping the bottle underneath the water, letting the bottle partially fill, then capping the bottle again under the water, taking the bottle out of the water, flushing the ambient water in the bottle, and then he's dumping the excess water downstream. This process is repeated 3 times. Uncapping the bottle underneath the water, letting the bottle partially fill, capping the bottle underneath the water, flushing the bottle, discarding downstream. Third time. Flushing the bottle, discarding downstream. Now the bottle is ready to be completely filled. Since this is an inorganic sample, we do not have to worry about headspace since there are no volatiles that will be analyzed in the inorganic sample. The bottle is then filled, and the sample is complete.
Samples are collected from the surface when water depth is less than about 10 centimeters. Since the water chemistry is somewhat different on the surface when compared with the subsurface, Sampling of shallow surface water should be noted on the field data sheet. Samples should be collected with the same methods as subsurface water samples unless the water depth is too shallow, and water must be poured from a small bottle to fill other, bigger sample containers. The material of the different containers does matter. Please move to the next screen for further details. When the water in the sampling reach is too shallow to completely submerge a given sample container underwater, alternative fill methods must be used. The pictures show surface water being collected in step 1 and then being poured into the desired sample bottle in step 2. This is repeated many times until the desired volume has been collected. Different types of bottles are laboratory cleaned for different analytes. Those sampling should be aware of which bottle type they are transferring from and into which bottle they are pouring. The bottle size and type will vary. Pouring should only occur from glass to glass or glass to plastic, but never from plastic to glass. Glass and plastic have different pore space and therefore are used to store different analytes in different ways. If you have preservatives or acid storage solutions in the small bottle, never use it to collect and pour water into another container. For further information on bottle types, sizes, and designated analytes, please see Appendix D of the Swamp Quality Assurance Management Plan. Waiting to collect samples using the subsurface grab method may be hazardous under certain conditions. Always be aware. Wear a life jacket or a personal flotation device if needed, and protect yourself. As always, make sure you have a buddy close by watching you. To determine if it is safe to wade, evaluate the current velocity in feet per second and multiply that number by the water depth in feet. If the magic number you get is more than 10, do not wade. For example, if you estimate a current velocity of 2 feet per second and the depth is 2 feet, the magic number is 4 and it is probably okay to wade. Please see more information about wading in the Health and Safety section in Element A. Click on the button to view a video on sampling safety.
One of the important things we need to know is whether or not it's safe to wade in any given watercourse. So there's a rather easy formula that we can use, and if we take the depth of the water multiplied by the velocity, and if that is greater than 10, it is unsafe to wade. So in a riffle, even though the water is very shallow, if it's moving very quickly, it could be very unsafe. So we need to take that into account before we decide to enter the water and take a sample. And a secondary consideration is taking a sample in swiftly moving water can be very difficult. And even though it may be safe to wade, if it is moving very quickly, when you take and reach down and put your hand in the water, you're going to get a bow wave coming up your hand, so you have to be cognizant of that.
In the previous topic, you saw how to fill sample containers directly while wading. The following two subtopics explain how to do the direct filling when you cannot wade and need to use devices that allow for extended reach. Extended holders shown in section 4.4.1 include a weighted basket that holds the container and can be suspended into the water from a bridge, or the pole with a clamp that holds the container and can be extended from the bank. Another variant of the direct filling principle makes use of an air displacement device which holds the sample container within its body and allows for sampling at a discrete depth. The intake parts need to be cleaned between stations. Examples described in section 4.4.2 include the Lamont sampling bottle or the isokinetic sampler. All of these examples make use of the first sampling principle, direct filling. Moving on to the second sampling principle, the bucket and beakers used to grab and transfer water are shown in section 4.4.3, and the trap and transfer devices based on the same principle are shown in section 4.4.4. Look for the icon in the top right corner. The third sampling principle is explained in section 4.4.5 with pictures of the peristaltic pump and an automated water sampler. Click on a subtopic or click Next to see them in order. These devices allow you to fill your sample bottle directly with the ambient water, even when you cannot hold it in your hands. The bottle is secured to a holder that lets you extend it into the water and retrieve it full. The pole sampler has a clamp that holds the bottle, and is particularly useful for small plastic containers. It is indispensable when you need to collect a sterile sample as seen in section 4.5.1. A pole can be extended from the bank, a dock, or a bridge, and if you use a telescopic pole, you can extend your reach even more. The perforated bucket sampler can hold larger and heavier glass bottles that you may need to fill for organics or toxicity tests, and it can hold more than one bottle at a time. The perforated bucket sampler is often used to collect water from bridges or hydromodifications. It is a great way to sample the centroid of the flow when there is no access from the banks. Please remember that when you stand on a road bridge that allows for traffic, you endanger yourself. Always wear a safety vest, use orange cones to mark your movement range, and avoid sampling at night if possible. If you must sample at night, put out various lighting devices. Click on the button to view the video on the use of the perforated bucket sampler.
This is a demonstration of a bucket sampler. Oftentimes there's limited access to the sampling reach where you want to sample. And there are bridges or hydromodifications where you can actually lower the bucket sampler off of to get a water sample. It consists of your sample bottle and a weighted bucket, where I'll put the bottle in the bucket. The bucket has weights on the bottom to make sure the bottle sinks enough into the water. One thing you want to note on this is that you are collecting a small amount of surface water in this sample because you're entering and exiting the water coming up through the surface. We'll take the cap off the bottle. Lower the bucket down. And just get enough water to where we can rinse the bottle. We'll have to rinse the bottle 3 times. Cap the bottle. Flush some of the ambient water around in the bottle, then dump the water downstream. We'll repeat this process 3 times so we can flush the bottle with ambient water. Good start. After the bottle has been rinsed 3 times, we then fill the bottle completely to the top. Cap the bottle. The water sample is complete.
There are air displacement devices that hold the container within their structure and allow you to collect samples from discrete depths for special purposes. A displacement device has an intake opening separate from the air outlet, and when lowered into a water column, water comes in through the intake, which is usually equipped with a pipe leading into the sample container. Air then escapes through the other hole in the ceiling or the wall of the container. Because sample water enters the container through an intake tube, the devices need to be cleaned thoroughly between stations. The item you see on your screen that looks like a hybrid between a bird and an airplane is an isokinetic sampler. Isokinetic samplers have a hydrodynamic shape and an intake nozzle that faces the current directly. Water pushed through the nozzle into the container is representative of the particulates suspended in the water. The sampler can be held with a pole from above while waiting, or it can be suspended by a cable from a bridge. Air displacement devices such as the Lamotte sampling bottle are used to collect samples for the Winkler titration of dissolved oxygen without contact with air. Click on the button to view a video on how the Lamotte sampling bottle can be deployed with a pole from the bank to collect water at a discrete depth.
Huh?
In some situations, the sampling methods shown in the two previous subtopics might not be appropriate because you need large volumes of sample or because you cannot obtain an extended sample container holder. A bucket tied to a rope is a readily available tool. It should be cleaned carefully before use. The bucket can be deployed from a bridge to collect a representative surface water sample from the centroid of the flow. Similarly, a beaker mounted on a pole can be used from the bank to reach the centroid, and a telescopic pole can extend the reach even further. In both cases, the devices can only be used to collect samples that are to be stored in plastic containers, because it is not recommended to transfer samples from plastic to glass. These devices are very useful when you plan to have many field crews collecting samples at the same time under unsafe flow conditions, for example during storm events, and if you plan to analyze the samples for conventional water quality parameters, nutrients, or metals. Please click on the button to view a video on the use of the pole and beaker device.
Okay, now we will be demonstrating the use of a pole sampler. In this particular case, the sampler is unable to wade into the water, and the water close to the sampler is unacceptable location for collecting a sample. We want to try to collect a sample in the centroid of flow, which is some distance from the bank. So the sampler will be using an extendable sampling pole with a container on the end, and in this case she can then access the centroid of flow. She rinses the sample container 3 times with the ambient water and then collects a sample and conveys it over to the person that has the actual sample container. He will then rinse the sample container 3 times in a similar fashion, and disposing of the rinsate water downstream and behind. And this is the 3rd rinse. Again, the sample container is agitated, and now the sampler reaches out into the centroid of flow with the extendable wand and takes the sample back to the person with the sample container. They then decant the sample into the sample container. The sample container is refilled, and then so that concludes our demonstration.
Water trapping devices have been used in oceanography and limnology for a couple of centuries to collect water from discrete depths. They are usually made of a metal or plastic cylinder equipped with rubber-coated plugs at both ends. Essentially, a cylindrical apparatus is sent into the water column while open on both ends, and a messenger that travels down the line causes it to close and trap the portion of the water column that it held. In other words, the device is sent down to the desired depth with the plugs held away from the cylinder, and then it is closed by activating the special closure mechanism. You may have heard of the Nansen bottle or the Van Dorn bottle. Please click on the button to view a video about the Kemmerer water trapping device.
Okay, I'm going to demonstrate the use of a discrete sampling device known as a Kemmerer water sampler. So the device is basically a hollow copper tube with 2 end seals made out of black rubber, and it is held open by a spring mechanism that slides on a rod that goes through the sampler, thus holding the 2 ends open to the water. The sampler is lowered to the desired depth, which is indicated by marks on the line. This is, you can't see it very well, but it's a black mark that's 1 meter. And when it reaches the desired depth, a brass weight called a messenger is lowered on the line. The messenger strikes the opening device and the sampler closes, trapping the water at that desired depth. Okay, I'm now going to demonstrate how to cock the sampler and get it ready for sampling. You simply remove the 2 end caps, pull it tightly, and the cocking mechanism locks onto the brass washer on top of the central tube and holds the end caps open. Now obviously the sampler should be properly cleaned and rinsed prior to use, and the assumption is that this particular one is. Now we will then lower the sampler off the side of the bridge, or if you're in a boat, off the side of your boat, down to the proper depth, indicated by markers on the line. When we reach the desired depth, the messenger, the brass weight, is released, sliding down the line and locking, closing the sampler. The sampler is then retrieved and the water is decanted using a spring-loaded valve in this fashion. After the sampler has been used, it should be cleaned and then stowed with the end caps not touching the interior of either tube, because you don't want dents to be forming in the seals. So the unit is placed back in the case, dried off, and stowed.
Pumps equipped with tubing are used to collect variable volumes of water from a discrete depth. Pumps can be easily constructed from available materials, such as a large syringe, tubing, and a three-way stopcock, or an inverted bicycle pump connected to a sturdy bottle that serves as a vacuum chamber into which the tubing brings the sample. Please contact the Clean Water team for more information about these devices. Battery-operated peristaltic pumps are used to pump water through a tubing set for sample collection. The tubing set can be pre-cleaned for the desired purpose. Samples are pumped and/or filtered directly into the sample container, touching only the tubing set. This prevents introduction of contamination by an intermediate sampling device. Pumps are very useful when you want to collect a depth-integrated sample. For example, when the water column is not totally homogeneous and you are interested in taking a single sample which represents the entire water column. You can move the tubing intake up or down the water column at a consistent speed while the pump keeps working. Automatic samplers such as the ISCO sampler also use battery-operated peristaltic pumps, but can be programmed to operate the pump and collect prescribed volumes of sample at given intervals, or in response to certain triggers, such as an increase in turbidity. Automatic samplers are installed in tamper-resistant shelters near the sampling site, and the intake tubing is usually led through a rigid pipe into the desired depth in the water. The sampler end of the tubing often leads to one big common sample container that combines all pumped subsamples into a composite, for example, a flow-weighed composite. More advanced models also provide a rotating arm, which moves the sampler end of the tubing to fill discrete sample containers at given time intervals, thus allowing one to track changes in concentrations of a given analyte over time. In many situations, the basic water sampling methods and devices shown in previous sections must be augmented by specialized techniques. For example, when you collect water samples for pathogen bacterial indicators such as E. coli or fecal coliform, you must use a sterile container to avoid introduction of bacteria from sources other than the sampled waters. This is demonstrated in the first topic. The second topic shows techniques that must be used if the analyses you plan will have very low detection limits, and consequently will be very sensitive to contamination. The ultra-clean sampling technique called clean hands, dirty hands is performed by two people and uses a procedure that minimizes contamination. Another set of special considerations is required when you collect samples for analyses of volatile compounds, and these are described in the third topic. Many swamp efforts include collection of microorganisms that contain chlorophyll A for subsequent extraction and quantification of that pigment in the laboratory, and the way to filter them out of the water and preserve them with dry ice is demonstrated in the fourth topic. When sampling water for bacterial counts, you can use sterile plastic 100 milliliter vessels, or sterile bags known as whirl packs. Either way, you need to familiarize yourself with the important things to keep in mind when handling sterile samples aseptically. Plastic vessels that are used to sample drinking water are sold with a small amount of sodium thiosulfate a reducing agent that is added to neutralize the residual chlorine present in the water so it does not kill the bacteria in the sample. Try to get containers without thiosulfate if you are sampling ambient waters. Always make sure that all the sample containers for bacteria are factory sealed. As best you can, avoid transferring sample liquids from another non-sterile container or sampling device. This may introduce bacterial contamination. If you can wade, collect the sample upstream of where you are by dunking in the stream. Remove the cap from the bottle just before sampling, and avoid touching the inside of the bottle or cap. If you accidentally touch the inside, discard it and use another sterile container. When wading into the stream, try to disturb as little bottom sediment as possible. Be careful not to collect water that has sediment from bottom disturbance. Stand facing upstream. Collect a water sample on your upstream side in front of you. If you cannot wade, attach your sample container to an extension pole and extend it from the bank to reach deeper water. Remember, no matter which type of sterile container you use, always fill it only to the 100 milliliter line and always leave airspace in the container. This is essential for thorough mixing of the sample at the lab. This topic shows one of the techniques that must be used if the analyses you plan will have very low detection limits, such as 0.01 micrograms per liter, or even below that range, and if you already know how and for what the data will be used. These low detection limits are often, but not always, required for trace metals, and are applied to samples collected during base flow when the water is totally clear. Samples for mercury require even more careful handling, because the detection limits are extremely low. We need to know about these minute amounts of mercury in water because mercury accumulates in organisms and its tissue concentrations increase over time and as we go up the food chain. Because of the high sensitivity of the analytical methods, contamination may be easily detected and interfere with the results, so the sampling needs to be done with extra precautions against contamination. The ultra-clean sampling technique, called clean hands, dirty hands, is performed by two people and uses a procedure that minimizes contamination. It follows EPA method 1666, sampling ambient water for trace metals at EPA water quality criteria levels. The next screen shows the most commonly used version of the clean hands, dirty hands technique. However, the reader is referred to the special PowerPoint presentation on the CD for details and additional information on sample filtration in the field. Use of the clean hands, dirty hands method involves very careful preparation in the lab. The sample containers are meticulously cleaned and acid washed, and then delivered to the field full of storage solution. Trace metal sample bottles contain 1% nitric acid, and mercury bottles contain 0.5% hydrochloric acid. Field operators should dispose of the storage solution into a waste container prior to sample collection, and have to wear polyethylene gloves when handling these bottles. The person designated as clean hands wears 2 sets of gloves and replaces the external gloves before taking each sample. It is assumed that ultra-clean sampling takes place in areas where you can wade. But if this is not the case, you can use a peristaltic pump with ultra-clean tubing, as shown later in this subtopic, or consult swamp experts on the best way to collect your samples. Click on the button to view a demonstration of sample collection using the clean hands, dirty hands technique.
In this clip, we will demonstrate the sampling technique known as clean hands, dirty hands. Peter, the sampler on the right, will be dirty hands. Sean, the sampler on the left, will be clean hands. Now, clean hands can touch only the sample container and wears double protection, in this case, 1 set of nitrile gloves and 1 set of poly gloves. Dirty hands requires only 1 set of poly gloves. And here you see dirty hands now donning the 1 set of poly gloves, clean hands on the left, making sure not to touch anything, waiting for dirty hands to glove up. When dirty hands is sufficiently gloved up, dirty hands then removes the sample pouch. It's a double bag. The sample bag, the inner sample bag, contains the sample container. The outer sample bag can be touched only by dirty hands, and then clean hands then can touch only the inner sample bag. Notice that the clean hands then removes the sample container, puts the clean inner sample bag back into the outer sample bag, Dirty Hands seals the outer sample bag and then presents the waste container to Clean Hands, who then removes the cap, pours the preservative into the waste container, and then recloses the sample container. Dirty Hands then replaces the cap on the waste container and stows it away. Clean Hands now goes to the sampling point, taking care not to open the sample bottle until the sample bottle is under the surface of the water. The sample is opened under the surface of the water and then rinsed 3 times with ambient water. Here, Clean Hands then performs the first rinse, empties the rinsate downstream, caps the container, opens the container underwater, and washes both the cap and the container very carefully. Again, this is repeated a 3rd time. Again, the container is capped, removed underwater, the bottle allowed to partially fill, the sample bottle is agitated to get a really good rinse, the rinsate is poured downstream, the sample bottle is again capped, placed underwater, the cap removed, and now the sample is collected. And here you see a close-up of the sample. Again, the cap being held in the Clean Hands right hand, the sample in the Clean Hands left hand, capped underwater, checked for headspace. The sample is then returned to Dirty Hands, who opens up the outer bag, and then Clean Hands removes the clean inner bag, opens up the bag, and very carefully puts the sample container in the inner bag. The sample container is put in the inner bag is closed, and then carefully pushed into the outer bag. Dirty Hands then seals the outer bag, and the process is complete.
A peristaltic pump can be used for ultra-clean sampling with special equipment. For example, you might need a Teflon tubing set. It can also be used with an inline filter. You will need to work with your laboratory to make sure that the pre-cleaning and assembling of collection kits are done according to protocol. Each component, be it a tubing set, filter, or sample bottle, should be stored in a new Ziploc bag to avoid possible contamination. To find out what Dirty Hands and Clean Hands need to do to flush the tubing set and collect a sample, and who needs powder-free polyethylene gloves, go to the PowerPoint presentation on your CD or the latest SWAMP standard operating procedures. Volatile organic carbon compounds include methyl tertiary butyl ether, or MTBE, benzene toluene ethylbenzene xylene combinations, also known as BTEX, gasoline components, and other volatile substances. The sample containers for volatile organics are a 40 milliliter dark glass vial. Because organic compounds tend to absorb the inner surface of a container, the sample container should not be rinsed with ambient water before being filled. In some cases, the vials are shipped to the field with a very small amount of 50% hydrochloric acid for direct preservation of the sample when the sample water is added. Naturally, these vials should not be rinsed with ambient water before being filled. If the vial has been pre-acidified for preservation, it should never be dunked either. In that case, collect the subsurface sample in a clean glass bottle and pour the sample to fill the vial quickly and without shaking. Note: if you expect samples with high buffer capacity or high pH, contact the lab and obtain materials and instructions needed to ensure that the pH is less than 2. Please click the button to view a video on how to fill the VOC vial from a large glass bottle.
The process for filling a VOC vial is, the beginning of the process is to fill one organics bottle with no headspace, which is the same method as doing a grab sample, which was demonstrated previously. You want to make sure that you fill the bottle with no headspace before pouring into the VOC vial. The VOC vial has a 0.5% hydrochloric acid solution preservative, just to make sure that the sample is preserved due to the short holding time. We then pour the sample into the VOC vial, making sure that we don't pour any excess water over the side. pouring a meniscus on the top. The bottle is then capped, making sure there's no airspace in the bottle. It's then flipped over and flicked to make sure that there's no bubbles in the bottle. The sample is complete.
Swampers measure chlorophyll A because it is a very valuable environmental indicator. Chlorophyll is the pigment that allows plants and algae to convert sunlight to organic compounds through the process of photosynthesis. Of the several kinds of chlorophyll, chlorophyll A is the predominant type in algae and is often used as a surrogate for algal biomass. Excessive amounts of chlorophyll A indicate the presence of algal blooms, which can lead to extremely high pH and dissolved oxygen values during the day, and to oxygen depletion at night or when the bloom collapses. On the other hand, too little chlorophyll A would mean that not enough fish food is available to fuel the food web. There are two approaches for sampling chlorophyll. In the first, you collect a large volume sample and separate the algae by filtration in the lab, while the second approach involves filtering the sample and then immediately freezing it in the field. The second approach is often called the chlorophyll A syringe method. Chlorophyll A is sampled by forcing water with a 60 milliliter syringe through a filter holder containing a 25 millimeter glass microfiber filter. The 60 milliliter syringe is rinsed 3 times with the ambient water before filtration. This screen shows you the equipment you will need to perform the sampling procedure: a container to fetch your sample from the stream, and your filtration kit, which includes glass fiber filters, a filter holder, a syringe, forceps, and packing materials to keep your loaded filters. Click the button to see a video that shows how this equipment is used.
This demonstration is going to be the procedure for the chlorophyll A sample collection and in-field filtering. The sample is collected from the centroid of flow along with the sampling protocols is followed with collecting all the other subsurface samples. First thing you're going to want to do, we're going to assemble the filter. This is the filter holder. Comes undone. There's an O-ring that you want to be aware of. It's helpful to get the filter a little bit wet. Helps the filter stick to it a little bit better. You gently take the filter out with the forceps and place it in the exact center of the filter holder, making sure it's secure. Place the O-ring on top also so it's centered, so you can put the filter together. And you want to take the syringe and get ready to filter your first 60 milliliters of sample. And you want to make sure you turn the sample through so it's well mixed. And you want to do that in between each collection. You put the filter in, and you want to make sure that as you're dispensing the water through, you carefully hold it in place, and then you slowly disperse the water. And the volume of water that you're going to put through the filter is going to depend on how much suspended particles are in the water. The more suspended particles, the less water you're going to use. So it's a judgment call. And you want to keep track of how much volume you're putting through the filter. It's something that needs to be recorded at the end. So for this sample, we're going to use 2 syringefuls, which is 120 milliliters. Okay. So again, recording the volume. You can also get an idea for how much volume needs to move through the filter based on the resistance you get as you're pushing the plunger. The more water you push through, the harder it gets to push through the filter. It's kind of an indication that you know you have enough water filtered. Then to prepare the sample, the filter, to go to the lab, you get a piece of foil. And an envelope. And the filter needs to be folded into quarters. Kind of use 4 sets. And you want to be careful when you're doing it not to squeeze all the water out of the filter. And put it into your labeled envelope, sealing it. Remembering to write the volume of water that was put through the filter. And in this case, we did 120 milliliters. And then we're going to take this back to the cooler and put it on dry ice.
Even a liquiding or subsampling of a sample that contains particulates is a challenge if the particulates are heavy and tend to sink fast. You can use one of the liquiding protocols for distributing the sample into receiving containers in small increments, repeatedly, to assure even distribution. You can also build or buy an liquiding device, such as the churn splitter shown on your screen. Click the button to go to Common Element C for more information about liquiding. The quality of the data you collect depends on the way that you collect it. As you perform your sampling activities, ask yourself at which steps you may introduce error or contamination. In this way, you will naturally figure out ways to prevent or minimize error. Common Element B also shows you how to affect, that is, control, check, record, and report the quality of your measurements and your samples. Beyond being aware and careful, there are several formal procedures to assure and check quality, and this topic provides information on those that are relevant to water sampling. The first subtopic describes ways to check the reproducibility, also referred to as the precision, of the sampling and analysis effort. The second and third subtopics show ways to protect sample integrity and prove lack of sample contamination. The issue of sample uniformity, which may be relevant during low flows or when moving patches of contaminated water are suspected, is addressed in the fourth subtopic. Field duplicates tell us about the reproducibility of the entire sampling and analysis process. Duplicate samples are needed for the generation of the precision data quality indicator, and this is essential for the delivery of data of known quality. It is very important to assure that the duplicates represent the same chunk of water, so that the difference between them indicates the error in our measurement process, not the natural variability. When weighting, duplicates are collected at the same time and place, side by side if possible. If you are using a pump, the duplicate sample should be collected at the same time by moving the output tubing between the two containers and alternating for several increments. If this is not feasible, collect the duplicate immediately following the primary sample. Field duplicates are currently submitted for swamp efforts at a rate of 5%, meaning that 1 sample out of 20 is collected in duplicate. If less than 20 samples are collected during an event, submit 1 set of duplicates per event. If you have used preservatives in the field, while sampling, or by addition of the preservative at the tailgate, your samples only need chilling. If necessary, certain types of samples will be preserved in the laboratory according to protocol for specific analysis, which will be acidification in most cases. Whether preserved or not, properly store and chill samples as soon as possible to prevent deterioration. Usually this is done immediately after returning from the collection by placing the containers on ice in a cooler within 45 minutes. Sufficient ice will be needed to lower the sample temperature to at least 4 degrees Celsius. Loose ice, also known as wet or crushed ice, is the most efficient in chilling the samples rapidly, but the use of wet ice must be temporary. Samples should never be allowed to swim in melted ice, because this is a sure way to introduce contamination. Some quality assurance quality control officers are now suggesting the use of frozen blue ice for the initial chilling as well as for shipping. The concave variety, designed to hug a beverage can, is probably the best option for small bottles. It is your responsibility to plan ahead and find out what you will need, depending on the sample volume, the anticipated outside temperature, and the sensitivity of the analysis, or its tolerance of contamination. Sample temperature should be maintained at 4 degrees Celsius until delivered to the laboratory. If this is a long process, consider refreshing the chilling devices if it does not interfere with custody seals. Care should be taken at all times during sample collection, handling, and transport to prevent exposure of the sample to direct sunlight. There are many types of blanks you will need to collect in order to prove lack of contamination, or assess the severity of contamination where it is not preventable. There are variations on the frequency and timing of blank collection, and each type of analyte or container may have its own protocol. You will be asked to collect field blanks, that is, to fill a sample container with clean water in the field, to show that your sample handling is clean. Travel or trip blanks are filled with clean water in the lab, and are taken to the field as is and back in the same ice chest as the environmental samples. Equipment blanks may be taken from the water that was used for the final rinse of the sampling equipment before it left the lab, or they may be the rinsets of sampling equipment after decontamination at the end of the sampling day. Different folks use different definitions, and you will definitely need to learn more about the specific analyte method combination that you will be sampling for. So please refer to the current Field Standard Operating Procedures appended to the Swamp Quality Assurance Management Plan. In most sampling events, you will need to fill more than 1 container of water at a given station, and all the containers in that set are considered one sample. Experience tells us that tracking sample containers, each with its unique collection time, may lead to logistical problems if the number of samples is big, and if they are grouped in sets that are supposed to represent one point in time and space. For this good reason, swampers usually write the same collection time on all the jars and bottles collected in one set of samples, that is, all the samples collected at the same station visit event. This useful practice is based on the assumption that what flows through a stream is homogeneous and does not change within the time it takes to collect all the containers. When the data goes into the central database, users assume that all sample containers sharing the same collection time and the same sample ID represent the same thing in the stream. So the hardness measured in the plastic bottle C can be used to assess the toxicity of the dissolved trace metals analyzed in bottle D. To accommodate the data user, field operators are asked to fill all the containers as close as possible to each other. However, actual filling times can be quite far from each other when you rinse each bottle 3 times, fill it, rinse the second container 3 times, fill that one, and so on. It is your responsibility to evaluate whether the concentrations might change quickly over time, and to use additional ways to increase sample uniformity if you need to. One way of doing this is to rinse all the containers with ambient water first, then fill them quickly. Fill them one by one as quickly as possible when using the direct filling methods. Use the principle of multiple increments if you are using any transfer or pumping sample collection method. When using a grab or trap sampling device such as a bucket, a beaker, or a chemerer, line up all the rinsed containers and transfer a little bit of water into each one, not necessarily filling them up, and then go back and get another grab. If you use a pump, move the tubing into each bottle for a short time, fill all of them partially, then start another round at the first bottle. Chances are that if you fill 20 to 33% of the bottle volume at a time, meaning going 3 to 5 times into each bottle, you will get a uniform sample even if there's high variability in what's going through the stream during the sampling event. Note that the same incremental transfer principle is also applied when you are splitting a sample to create aliquots or subsamples. And check out Common Element C, section C.2.3 for more information.